Welcome to the lectures on deep learning in artificial neural networks. In this video, I will discuss Dropout. I will introduce the method and then I will give two different interpretations. Dropout is a method of regularization. Remember that we want to use regularization methods if we have a network, a deep network of multiple layers, which in principle is too flexible given the amount of data we have. And then we want to regularize the network. We want to make it more stable. And this is how Dropout works. You start with a network with many hidden neurons, with many layers, a network that's very flexible. And then in each run, whenever you present a pattern, you remove half of the neurons. You remove half of the neurons. So this is how it works. For example, you choose a pattern number mu, and then you randomly suppress 50% of the hidden neurons during the training. So we would suppress for this pattern this set of neurons. Then we pick the next pattern and we suppress another subset, 50% of hidden neurons. And for the third pattern, we suppress another subset of hidden neurons. So in each version, for each pattern, we suppress a different subset of hidden neurons in the network. But now for testing, you use the full network with all the hidden neurons. But that would mean that a neuron that previously got input from n½ neurons now gets input from n neurons. And that's why you multiply the output weights by a factor of 1/2, so that the total input to this red neuron is roughly the same during testing as it was during training. Dropout is a very, very effective method for regularization in deep neural networks and widely used. There are two different interpretations of that method. The first interpretation is, well, it's an approximate but very practical implementation of bagging. However, there are several differences between Dropout and standard bagging, and you should be aware of these differences. Well, the first one is, if you do bagging, we train different models and then we just combine the output of these models. We average over the outputs. Not here. Dropout, not bagging, but Dropout is some method of doing something similarly to bagging, but in the hidden layers. Second difference. Normally, each configuration of bagging, each of the k repetitions of the models would be trained on a different but fixed database. That's not the case for Dropout. We have many different Dropout configurations. If you imagine that you have n hidden neurons, you randomly suppress half of them, well, try to count the different configurations. There are many configurations. And each of these configurations is trained with one specific input image, or maybe one specific mini batch of input images. And it's very rare that the same Dropout configuration would come back for a second image or a second mini batch. And if it comes back, it wouldn't be the same. Third difference. In bagging, the different models are independent. Not here. The different models share weights. In fact, half of the neurons are shared between one configuration and the next Dropout configuration. And the final difference, in bagging, well, we only consider the output and then we would average over the output or take a majority vote over the outputs. Well, that's also not exactly what we do here. We do it at the hidden layers. And at the hidden layers, we don't have simple averages. We have neurons that implement sigmoidal gain functions. Now let's come to the second interpretation. The second interpretation is Dropout implements some sort of forced feature sharing between neurons in the same hidden layer. Let me try to explain this. Well, we focus on this red neuron. It receives input from 4 neurons in the hidden layer, just one layer below. Each of the neurons in that layer implement a feature. They implement a hyperplane, and if this is the first hidden layer, we can really think of the hyperplane as the space of inputs. And then this would just be a hyperplane that separates the positive examples from the rest. Now the second neuron also implements a hyperplane. The third neuron as well, and the fourth neuron as well. And so what the red neuron implements is something like this smooth interpolation between these different hyperplanes. So far, standard implementation, standard training. But now we do dropout. Dropout means that we take twice as many neurons, but then we make sure that they all solve some similar tasks. And the way we do this is we say, okay, there are extra neurons coming in, we suppress some other neurons, and now these extra neurons, they have to replace some of the existing neurons because they will be gone. So we put in these extra hyperplanes, and the effect is that because each time when we put in extra neurons, we have to replace some of the existing things, but in all different combinations, all these, any subset of 4 hyperplanes out of the 8 hyperplanes needs to be a robust representation of this cloud of data points. And so they have to do somewhat similar stuff. They have to implement similar hyperplanes, and that means they have to implement different features. And that's what I mean. Dropout forces a lot of neurons in the same layer to share features, to do similar stuff, not exactly the same, but to do similar separations. They learn similar hyperplanes. In summary, there are 2 different interpretations of dropout. The first one is, well, dropout is just an approximate but very practical implementation of bagging. The second interpretation is the one that I like a lot. I really like to think of dropout as a tool to enforce representation sharing in a given layer of hidden neurons. Whatever the interpretation you prefer, in practice, dropout is a very useful regularization method specifically designed for deep artificial neural networks, and its advantage is it's simple to implement.